Hi everyone, I'm Sandeepa Bhunya. I'm a PhD student in the High Performance Computing Lab at Penn State University. Today, I'm very excited to talk about our work end-to-end characterization of game streaming applications on mobile platforms. Video games have tremendously evolved over the past few decades. The games have moved from arcades to consoles and to personal computers. The gaming industry has grown to rival and outpace the film and television industry. It has become an ever growing tsunami ever since the mobile gaming took off. According to a study released by Visual Capitalist in 2020, out of the overall $165 billion gaming revenue, $85 billion can be attributed to mobile gaming. However, if we compare the state of the art mobile games with their desktop PC versions, they're still lagging behind, as we can see from the two versions of the same game rendered using desktop GPU on the left and another rendered using the mobile GPU on the right. We can clearly see that the one rendered using desktop GPU has much more texture details and is more photorealistic compared to the mobile version. The mobile GPUs are yet to render such advanced graphics games. This is because they are resource constrained and have limited power budget. Recent emergences of several cloud gaming platforms such as Google Stadia, Nvidia GeForce Now, Microsoft xCloud, and others have salvaged the situation by streaming advanced graphics contents to mobile users. However, these cloud gaming apps, which we also refer to as game streaming apps, are known to be bandwidth heavy and latency sensitive. Luckily, the introduction of 5G, which promises Gbps data speed and sub-millisecond latency, has revolutionized 4K gameplay on mobile devices. However, there is a limited understanding of how these apps perform on mobile devices. Towards this, in our paper, we work to address the question, do the existing mobile devices run these cloud gaming apps efficiently? First, let us understand the architecture of the cloud gaming apps and the associated challenges. In a typical game streaming pipeline, the game engine, labeled as 1 in this pipeline, comprises of the game logic, which evaluates the next state of the game environment and invokes graphics API calls to GPU to generate or render the next frame. As a raw rendered frame is large, it is compressed or encoded before it is transmitted to the client. At the client, the received encoded frame is then decoded and stored in a frame buffer. The client display processor then fetches and displays it on the user screen. During gameplay, the user interactions are captured by the client and transmitted back to the server. The game engine then integrates these user inputs into the next game state evaluation and frame generation. This pipeline might appear same as the video streaming pipeline. Although the client end stages of these pipeline are same, however, unlike video streaming where the video frames are pre-encoded offline and stored and can be reused by several clients later, the cloud gaming apps are real-time and interactive in nature. Hence, their frame generation and encoding occurs during the gameplay. There are several challenges involved in running these cloud gaming apps on mobile platforms and performing profiling studies. First concern is the faster battery drain. Although 5G unleashes tremendous performance perks of high-speed Gbps internet, but it comes at the cost of huge battery drain. Our profiling shows around 1 hour of 4K gameplay on a Google Pixel 5 phone using 5G can drain 36% of battery. The next challenge is the observed degradation in QoS. Quite often, playing 4K cloud games on mobile suffers from low frame rate and reduced video quality. Since these apps are interactive in nature, the bottleneck could be anywhere. It could be at the server, the network, or the client. Therefore, it is critical to understand the end-to-end performance and energy behavior of cloud gaming apps. However, carrying out such characterization study is a non-trivial task, as it involves parameter sweeps across a large space such as graphics fidelity, encoding quality, frame resolution, network type, or game genre. Next, let's move on to our evaluation methodology. The first and foremost step was to choose the right platform for performing the characterization. As the popular cloud gaming apps are proprietary in nature, both the client and server pipeline stages are viewed as black boxes, which makes them implausible for profiling. Hence, we choose an open source game streaming client app for the Android OS called Moonlight Game Stream for our studies. It presents a graphical UI on the client device which captures user input and sets up communication with the server. The open source nature of this client app enables modification of the client and application pipeline for profiling purposes. Furthermore, the user can set up their own server equipped with GPUs, thus making the server pipeline stages and network statistics observable. Moving on to details of our game stream evaluation framework, the server and client communicate via the NVIDIA Game Stream protocol, with the server-side communication handled by the NVIDIA GeForce Experience app installed at the server and the client side by the Moonlight Thin Client app at the client. To profile these pipelines, we annotate the Moonlight source code to collect several statistics such as sending frame rate at the server, the incoming receive rate at the client, network latency, frame drops due to network, per pipeline stage latencies at the client, game video packet details, and etc. The methodologies and tools for collecting server-side per stage latencies are described in details in the paper. Next, moving on to our gaming workloads and characterization results. We set up a high-end workstation with Intel i7 core equipped with NVIDIA GTX graphics cards as our server and a Google Pixel device equipped with Gbps range 5G millimeter wave frequency bands as our client. Our gaming workload was selected from various genres based on amount of texture or game scene details and amount of motions in the game scenes or scene variations. We use 7 games in our study listed in the table here. We conduct a thorough parameter sweep across various tunable parameters for the game streaming pipeline. We consider different graphics setting and rendered frame resolution for the game engines. We also fiddle with different encoding bit rates and frame resolutions at the server encoders. We also evaluate the impact of two types of network connection, that is 5G and Wi-Fi, on game streaming. We quantify the QoS and performance by measuring the frame rate and game video quality. And finally, we measure the power and energy consumption of the client devices with respect to different network types, encoding bit rates, and game types. Our first goal was to determine whether each individual stage of the game streaming pipeline is able to generate frames at a 60 FPS throughput or not. To this end, we start by studying the effect of network types on the frame rate. First, we study the frame drops due to 5G network. Here we consider the 4K gameplay of Destiny 2 game when encoded at different bit rates. The orange line plots the video stream frame rate from the cloud renderer, and the gray line plots the incoming frame rate received from the network by the client. The area between the orange line and the gray line represents the average frame drop. We observe that as the encoding bitrate is increased to 50 Mbps, the frame drop increases to 4.8% compared to negligible drops when encoded at 40 Mbps. It can be attributed to two factors. First, increase in network latency, which is in turn due to the increase in encoded frame size as the bitrate is increased. Second, due to increased packet loss, which happens due to buffer overflows, which in turn can be attributed to the congestion in the in-network 5G buffers. Furthermore, as the 5G millimeter wave operates at high gigahertz frequencies, they are more susceptible to penetration loss, which further exacerbates the packet loss. Next, we studied the frame drops when using Wi-Fi network using the same encoding bit rates as the 5G study. We observed that the frame drops increase significantly even when the game video is encoded at low bit rates compared to 5G. This is primarily due to insufficient Wi-Fi bandwidth compared to Gbps range bandwidth offered by 5G. These studies highlight the significant facets of network technology, which can be a potential bottleneck for the QoS frame rate. Next, we ask the question, assuming ideal network connection, can the user still observe a drop in the frame rate? To address this, we study the QoS frame rate at the server. We begin by looking at the frame generation at the rendering stage in the server. Towards this, we collect the frame rendering time for the games at 4K and 1080p resolution and at different in-game graphic settings where LG stands for low graphic settings and HG stands for high graphic settings. The 60 FPS deadline translates to 16.66 millisecond rendering time. The lower the latency, the better is the QoS. The games are clustered according to their graphic settings, with the 3D rendered games in the right and the 2D rendered games in the left. The rendering time for each of the setting is represented in the green asterisk. The key observation is that when rendering graphics intensive games at 4K, all of them fail 60 FPS deadline. This was mostly due to the increased complexity of 3D object rendering as well as increased computation due to the rich texture content in these games. Note that the 2D rendered AOE 2, that is the Age of Empire 2, also suffers from reduced frame rate. On further examination, we found that this was due to their inefficient game engine design leading to graphics draw calls spending more time in the rendering queue. Next, assuming the ideal frame generation performance at rendering stage, we next investigate the frame rate at the next stage in the game streaming pipeline, that is the encoding stage. Towards this, we collect the frame encoding time for 4K and 1080p games encoded at 3 different encoding qualities, high, medium, low, represented by the cluster of 3 bars. We observe that the encoding time exceeds the 16 millisecond deadline for most of the 4K resolution games, irrespective of their graphics fidelity. Instead, the encoding latency correlates with 2 factors. First is the encoding quality level. We observe that across the games and frame resolution, demanding a higher encoding quality leads to a higher encoding latency. Second is frame resolution. For any game, as the frame resolution is increased from 1080p to 4K, there is an increase in the encoding time cluster. Hence, the encoding stage is the major bottleneck in the game streaming pipeline. The next question we want to ask is, assuming ideal performance at server and network, can the client still observe reduced frame rate? To study the QoS frame rate at the client, we collect the decoding time of the received frames. The lower the latency, the better is the QoS. Across all the games, the decoding time mostly depends on the frame resolution and the encoding bitrate. Further, the 4K decoding time increases as the bitrate reduces. Especially, higher frame drops are observed when decoding higher frame resolution at low bitrate. For example, when decoding a 1080p resolution frame which is encoded at 10 Mbps bitrate, we observe no frame drop, whereas when decoding a 4K resolution frame encoded at the same bitrate, we observe around 15% frame drop. This is mostly due to when encoded at low bitrate, higher frame resolutions require more computation to decode the frame. To measure the power and energy consumption at the client device, we collect the power profile of the client device when playing the Destiny 2 game at 4K resolution encoded at 20 Mbps bitrate and compare when using 5G network with that with Wi-Fi network. We can clearly see that the power consumption is significantly higher when using 5G than when using Wi-Fi. Similarly, for the energy breakdown, we break down the overall energy consumption across three main components, that is the network, display, and the decoding units in the client device. And for Wi-Fi, when using Wi-Fi, we can clearly see that the energy bottleneck shifts to the decoding stage. That is, it attributes to around 73% of the overall energy consumption. Whereas when using 5G, the network processing energy dominates, which is around like 7.5x more than when it was using Wi-Fi. Furthermore, on further examination, we also found that the most power-hungry component in the 5G network subsystem is the millimeter wave antenna module. Detailed explanation can be found regarding this in the paper. More power and performance results for all games and their detailed descriptions are in the paper. Based on these observations, we propose a client-aware QoS and energy optimization scheme where the client shares the frame drop statistics, remaining battery percentage, network conditions, and user preference to the server along with the user inputs, so that the server can utilize these runtime information from the client to dynamically modify game visual settings, encoding bitrate, frame resolution, based on the user preference, which can be of two flavors: for best gameplay experience at the cost of battery drain, and for prolonged gameplay experience at the cost of reduced QoE. Finally, summarizing our observations, we perform a comprehensive performance and power analysis of game streaming pipeline across server, network, and client. At the server, the rendering and encoding stage consumes significant latency, missing the 16.66 millisecond deadline, thus suggesting novel hardware and software optimizations necessary to accelerate these stages. At the network, streaming at higher bit rates using 5G suffers from significant frame draws due to congestion in 5G network buffers. Furthermore, lossy 5G signals further exacerbate the situation, thus demanding the need for intelligent data distribution frameworks and optimizations to mitigate the 5G in-network buffer congestions. Further, a coordinated design supporting variable bitrate between server and client is essential for real-time and interactive applications such as the cloud game applications. Finally, at the client, the 5G network module is the most energy consuming component, which consumes about 51% of the total energy, thus indicating the need for energy efficient 5G network module designs for mobile clients. With this, I come to the end of this talk. Thank you so much for watching the presentation. Looking forward to your questions and meeting you at the conference.